Hi, and welcome to AP Chemistry Review. It's me, Dr. V, and it's a good day to review for the AP Chemistry exam. I think every day is a good day to review for the AP Chemistry exam. In this webcast, we're going to be talking about the first free response question from the 2022 exam. The first free response question in any AP Chemistry exam is a long question, meaning it's scored out of 10 points and has multiple parts. Sometimes there are 8 or 9 parts to a 10-point free response question in AP Chemistry. I recommend that you get your calculator and your periodic table and your AP Chemistry equation sheet, plus some paper. I want you to use this webcast as an opportunity to practice. I'm going to introduce each part of the problem, and then I want you to pause the webcast, try to answer it yourself, and then listen to my explanation. And then you can keep score of your own work as you go. Did you earn the point or did you not earn the point? And the advantage of working this way is that it helps you get better as a chemistry student, and this is how you'll learn how to write higher quality, more informative free response answers. So you maximize your points and you can show off all that great chemistry knowledge you've got. Let's jump right into the problem. A student reacts 0.3 grams of methyl salicylate, which has the formula CaH8O3, with a stoichiometric amount of a strong base. This product is then acidified to produce salicylic acid crystals, which have the formula HC7H5O3. Part A says, for every mole of methyl salicylate that reacts, 1 mole of salicylic acid is formed. Calculate the maximum mass in grams of salicylic acid that could be produced in this reaction. What you might be noticing is that we weren't given a balanced equation. Don't panic, it's okay. There's a plan. If you read Part A carefully, you'll notice you're given a mole-to-mole ratio. For every mole of methyl salicylate that reacts, 1 mole of salicylic acid forms. So we have this 1-to-1 mole ratio. So we don't have the balanced equation, but we actually have the information that we need to solve the problem. This is a theoretical yield calculation. I've got the mass of one reactant. I need the mass of the product. And so we're going to set it up as factor label. Before we start doing that, notice we are given the starting mass of the methyl salicylate. So we have that in grams. We want to know the grams of the salicylic acid. And conveniently, we were given the molar masses of both methyl salicylate and of salicylic acid. And so we can set it up grams to moles to moles to grams and do our calculation out. So let's jump right into that. How many grams of salicylic acid will I form when 0.3 grams of methyl salicylate react completely? So I'm going to take my grams of methyl salicylate, turn it into moles. I'm going to use my mole-to-mole ratio to find moles of salicylic acid, and then I'm going to use the molar mass of salicylic acid to find the final answer. So I set that up. All the units cancel out the way I want, and I'm left with a mass of salicylic acid, which comes out to be 0.272 grams of salicylic acid. I do want to point out that we're reporting our answer here with 3 sig figs, because our starting quantity had 3 sig figs, and our molar masses had more than that. That's not the major focus of this part, but we still want to be careful and pay attention to those details. Part A was scored for 1 point. Either it was done correctly or it wasn't. Either you had enough work and a correct answer, or you didn't. I do want to remind you, always make sure when you're doing a calculation that you show a complete setup for the calculation and not just the answer. If all you have is an answer that appears out of thin air as far as the readers are concerned, you're not going to get the point. The problem continues. As part of the experimental procedure to purify the salicylic acid crystals after the reaction is complete, the crystals are filtered from the reaction mixture, rinsed with distilled water, and dried. Some physical properties of salicylic acid are given in the table, and this is going to become very useful to us. We'll make sure we keep referring to it. The student's experiment results in an 87% yield of dry salicylic acid. The student suggests that some of the salicylic acid crystals dissolved in the distilled water during the rinsing step. Is the student's claim consistent with the calculated percent yield value? Justify your answer. I want to point out that the College Board really likes questions where you have to do error analysis and talk about whether this error could have contributed to the results that you're seeing. So that fits right in here. Also, I want to just remind you of the use of the word justify here. In AP Chemistry land, that means one of 3 things. It means you're doing a calculation to back up your answer. You're using math-based reasoning, but not necessarily a calculation to back up your answer. Or you're referring to some experimental data as part of your answer. In this question, we're asking, would the rinsing step lead to a percent yield that's less than 100? In the table, we're told that salicylic acid has a measurable solubility in water. We can dissolve 2.2 grams of salicylic acid in a liter of water. And just to remind you, percent yield is the ratio of actual over theoretical yield. We calculated the theoretical yield in part A, so we know what that is. We know what that should be. So really what we're trying to figure out is, would this rinsing step affect our actual yield? And the answer is yes. The student's claim is consistent. Salicylic acid will dissolve in water to some extent. If some of the salicylic acid dissolves in the water of the rinsing step, you're not going to recover all the salicylic acid as a solid. Some of it will still be in the water. And that means our actual yield is going to go down, right? When we go to measure the mass of those dry crystals, it's going to be smaller than what it really should have been. And because the actual yield went down, that means the percent yield is going to go down. And so we can back this claim up. I do want to remind you, when you're doing these kinds of problems, to lead with the answer and then state your justification. It makes it easier for us to find all the information. This question was scored out of 1 point. Either you backed up your answer with a correct claim or you didn't. Part C says, given the physical properties in the table, calculate the quantity of heat that must be absorbed to increase the temperature of a 0.105 gram sample of dry salicylic acid from 25 degrees Celsius to the melting point of 159 degrees Celsius and melt the crystals completely. So we need to think about, how much energy do I need to put into the salicylic acid to do this? There are actually two parts to this in terms of the calculation we need to do. I need to take it from 25 degrees up to 159 degrees. So I have to heat the sample and change its temperature. And then I have to melt it. So there are two steps. I have to heat the solid from 25 degrees to 159. And then we know that the melting point's at 159 degrees, and I'm going to have a phase change, and I need to incorporate that. So I need to heat the solid and then melt the solid. I like to do these kinds of problems by drawing a little temperature versus time graph to help me keep track of all the parts of it. So there's a calculation for heating the solid, right? Which I'm going to call that Q1. And because the temperature is changing, I'm going to use MC delta T for that calculation. And then I have a phase change. I'm going to call the calculation for the energy to melt the solid Q2. And for that, we use the mass times the heat of fusion. So I have two segments in my temperature versus time graph. I have two calculations that I need to do. In order to finish the question, I need to add the values from Q1 and Q2. So let's go through these calculations. So for Q1, calculating the energy required to heat the solid from 25 degrees Celsius to 159. I have to use the specific heat capacity of the solid, which we're told is 1.17 joules per gram per degree Celsius. And I also want to point out that the mass of the sample is 0.105 grams. We're not using our answer from part A here. So I'm going to substitute in the mass and the specific heat and the delta T, which is T final minus T initial. So 159 minus 25. And I'm going to then calculate that, and I get an answer of 16.5 joules. It does have 3 sig figs. And now I need to calculate the energy to melt the solid, where I use the mass times the heat of fusion. And again, we're given the heat of fusion, but I want to point out the units for that. It's in kilojoules per mole, and we knew the mass of the sample in grams. We need to make sure that we have units that match up. The easiest way, I think, to do this is to take the grams of the solid and convert it to moles. We do know the molar mass. So to calculate Q2, I'm going to calculate the moles of salicylic acid. So I'm going to take 0.105 grams and divide by the molar mass of salicylic acid, and then multiply by the heat of fusion. Now that is going to give me an answer in kilojoules with 3 sig figs. And of course, we know to get the total energy, we need to add Q1 and Q2. But Q1's in joules, and Q2 right now is in kilojoules. They really need to be in the same unit before we add them up, or this won't make sense. So I'm going to take my kilojoules and multiply it by 1,000 to turn it into joules, which would be 20.6 joules. And so to find the total energy required to bring about this change, I'm going to add Q1 and Q2, and I get 37.1 joules for my total answer. Now, in terms of the scoring for part C, it was worth 2 points. There was 1 point for correctly calculating Q1 and Q2. If you made a mistake in either one of these, you did not get that point. And then the second point was for correctly adding them together and recognizing that you needed to do that. The problem goes on. The structures and melting points for methyl salicylate and salicylic acid are shown. And we were given the formulas and we're given their melting points. Part D goes on and says the same three types of intermolecular forces, namely London dispersion forces, dipole-dipole attractions, and hydrogen bonding, exist among molecules of each substance. Explain why the melting point of salicylic acid is higher than that of methyl salicylate. The College Board does love questions where we've got two different substances, and based on differences in melting points or boiling points, we're explaining the differences there based on intermolecular forces. So this is a real kitchen sink question. It's got a little bit of everything. What I want you to remember, and not just for this problem, but for any problem where you're asked to do that, the substance with the higher melting point or the substance with the higher boiling point has the stronger intermolecular attractions. If you're given that data, you need to use it. We're told here that methyl salicylate has a lower melting point than salicylic acid. Well, why? We know they both do London forces, dipole-dipole attractions, and hydrogen bonding. Their molar masses are pretty similar. They both have similar functional groups. So how can we explain this? I think the best way to explain this really comes down to hydrogen bonding. Both molecules can do hydrogen bonding. If we look at both molecules, each of them have 3 oxygen atoms that could accept a hydrogen bond from another molecule in the sample. The methyl salicylate has 1 hydrogen atom that can form a hydrogen bond with another molecule on another molecule's oxygen, for example. But salicylic acid has 2 hydrogen atoms that could form hydrogen bonds with another molecule. And so I've got more sites for hydrogen bonding with salicylic acid than I do for methyl salicylate, and that's the basis of our answer. Since salicylic acid has more hydrogen bonding sites than methyl salicylate, the intermolecular forces between salicylic acid molecules are stronger than the IMFs between methyl salicylate molecules. And all this was 1 point. Either you had a correct answer, a correct explanation, or not. You probably could write it with fewer words, and that would be fine. Bullet points are great. You don't need to do complete sentences, but you do need to have accurate descriptions. The problem goes on. The student titrates 20.0 milliliters of 0.01 molar salicylic acid with 0.02 molar NaOH using a probe to monitor the pH of the solution. The data are plotted producing the following titration curve. This question is all over the place. We did some stoichiometry, then we did IMFs. All of a sudden now we're doing titrations. It all kind of fits in though. There's a lot of stoichiometry in titration, so it's not an unreasonable progression. Part E says, using the information in the graph, estimate the pKa of the salicylic acid. At this point, as you're reviewing for the AP Chemistry exam, it's important for you to know that at the half equivalence point of a titration of a weak acid with a strong base, which is the situation we have here, the pH of the solution will equal the pKa. Looking at the graph, we can see that it takes about 10 milliliters of the NaOH, the titrant, to reach the equivalence point. And we know that because that's where we have that really sharp rise at about 10 mils. That's our equivalence point. So the half equivalence point would be at about 5 mils of added titrant. So we need to know the pH at the half equivalence point, which is just over 3. So your answer for the pKa needs to be about 3. This was a 1-point part. Either you had a pKa of approximately 3 or you didn't. You didn't have to write out an explanation. You just needed to write that the pKa is about 3. You might have said 3.1, that's fine. Let's talk about this titration curve some more in part F. When the pH of the titration mixture is 4, is there a higher concentration of the weak acid, salicylic acid, or its conjugate base, salicylate ion, in the flask? Justify your answer. Let's go back and look at the graph. I'm going to claim that there's a higher concentration of the conjugate base in the flask. How do I know this? How do I back it up? At a pH of 4, I've added about 9 mils of sodium hydroxide. I'm almost at the equivalence point, but not quite. What we see, though, is that the pH of the titration mixture at this point is greater than the pKa that we calculated in part E. We know that the pKa was about 3. So if the pH is greater than the pKa, I must have more conjugate base than I have weak acid. And these are relationships that you really need to know. And I needed to use that kind of reasoning to earn the 1 point for this part. There is another way to answer this question. You could have also said, I'm beyond the half equivalence point, so I've used up a lot of my weak acid, the HA, and turned it into A-. So I should have more conjugate base than weak acid in the solution. That would also get full credit. But we're not done. Part G says, the student researches benzoic acid and finds it has similar properties to salicylic acid, which is what we've been talking about. The Ka for benzoic acid is 6.3 times 10 to the minus 5. Calculate the value of pKa for benzoic acid. The definition of a pKa is that's the negative log of the Ka value. So all we have to do is substitute and evaluate. So it's the negative log of 6.3 times 10 to the minus 5. And I'm going to do my calculation, and I get 4.2 up. I do want to point out that since my Ka value had 2 sig figs in it, I'm going to report my pKa with 2 digits after the decimal. Trying to be careful about my sig figs here. The sig fig rules are always a little different when you're working with logs. This was worth 1 point. Either you had a correct calculation with a setup to support your answer, or you didn't. We've got one more part. The student performs a second titration, this time titrating a benzoic acid solution with the 0.02 molar NaOH. Sketch the curve that would result from this titration of benzoic acid on the graph, which already shows the original curve from the titration of 20.0 mils of 0.01 molar salicylic acid. And we're given one other piece of information. The initial pH of the benzoic acid solution is 3.11. So the dash curve was the data from the previous titration that we were just talking about, and we need to draw in a new titration curve for benzoic acid. One thing I want to point out is notice that the volumes of the 2 weak acid solutions are the same, and the molarities of the 2 weak acids are the same. This is important because it tells us that it's going to take the same volume of NaOH to reach the equivalence point for this curve compared to the curve we already have. We were also told that the initial pH of the benzoic acid solution is 3.11. So I'm going to start at a slightly higher pH than the dash curve that we see here. The other thing we have to keep in mind is we know the pKa of the benzoic acid solution, and so we need to incorporate that as well, because we know at the half equivalence point, the pH equals the pKa. So our graph has to incorporate all these things. Here's what your graph should look like. You're going to start at just above 3. I got to use my rainbow pen. That always makes me happy. I need to have my equivalence point at 10 mils, and I need to make sure that I have the half equivalence point with a pH of 4.2. 3 key features in your graph. Start at the correct pH. You're told it's 3.11. Make sure you've got that. We knew that the pKa is 4.2, so at 5 mils of added NaOH, I need to be at about just over 4 with my new pH curve. And the third key feature that we're looking for is at the equivalence point, so the vertical part of my pH curve is at 10 mils of titrant, and then it's going to level off at pretty much the same point as the last one. Part H was scored for 2 points. The first point required you to hit both key feature 1 and key feature 2, that you started at the correct pH and that you had the correct pH at the half equivalence point. If you missed either one of those, you could not earn this point. And to earn the second point, you had to have your equivalence point at 10 mils of titrant. And that's what we're looking for in this problem. So you're really showing that you understand what's happening in a titration curve. You're showing an understanding of the stoichiometry of the problem, and that you've got a weaker acid. Everything's going to be bumped up a little bit. So how did you do? Tally up your score out of 10 points. In 2022, the average score on this question was 4.44 points out of 10. So if you scored 5 points or above, you're doing well. If you found this video to be helpful, like the video and leave me a comment. And make sure you subscribe to my channel so you get all my latest updates. It's always a good day to study chemistry. Keep working on it. You're going to get better and you're going to do well.